In this lab, I attempted to model the motion of a multi-particle system using the momentum principle and the energy principle. I recorded a video of two marbles of different masses and initial velocities colliding in one-dimensional space and measured their resulting velocities and momentums. Then, assuming no energy escaped the system to the surroundings, I constructed a computational model that used the idea of conservation of momentum to predict the marble's motion after the collision. After comparing my prediction to the observed data and calculating the change in the system's kinetic and thermal energies, I found that the actual motion was underpredicted by the model and that, as a result, there must have been some net escape of energy from the system to the surroundings, most probably in the form of a thermal energy increase of the table the marbles were rolled on. According to Newton's second law, if the net force on the system is zero, then the total momentum of the system is conserved regardless of the interactions that occur internally. I took the system to be the two marbles in this video, so the net force on the system consisted of the gravity force due to the Earth and the contact force due to the table. The perpendicular component of the contact force was equal in magnitude to the force due to gravity, so the perpendicular part of the net force was zero. Since the table was relatively smooth, I made the assumption that the parallel component of the contact force, the force due to friction, was negligible. I later found, as I will explain presently, that this assumption was probably not completely true and was likely a cause of the discrepancies in my data. In order to measure the total momentum of the system before and after the collision, I tracked the position data from the video and measured the changes in position with respect to time for each marble. The total system momentum was simply the sum of the momentum of the first marble and the momentum of the second marble. According to the principle of conservation of momentum, any momentum lost by the large marble after the collision was transferred to the smaller marble, so the sum of the new respective momentums was the same as the sum before the collision. Using this principle, I constructed a computational model in VPython of the two marbles. I input the initial velocities of both marbles as well as the velocity of the large marble after the collision, and then told the computer to calculate the predicted velocity of the small marble after the collision. In order to calculate these initial velocities, I used the first and last positions of the marbles before and after they hit each other, and calculated their rates of change of displacement with respect to time. I assumed that the marbles were experiencing constant velocities throughout, except of course during the actual collision. To predict the change in velocity of the small marble, I solved the equation relating initial total momentum to final total momentum for the final velocity of the marble. Then I added this relation into the code, telling the initial velocities to change to the final velocities when the distance between the large and small marbles' positions was zero. This was when they collided. I had the marbles' expected positions exported to a spreadsheet, which I then compared to the actual positions of the marbles. As can be seen by this graph, the predicted speed of the small marble after the collision was greater than the actual speed of the marble. The final velocity calculated by the model had a higher magnitude than the observed final velocity, and thus the momentum of the small marble was also overpredicted by the diagram. I graphed the velocities and momentums of the marbles as well, and it is evident that some of the momentum was lost from the system, and thus was not conserved as expected. In order to determine why the marble's motion was not consistent with the law of conservation of momentum, I reevaluated the conditions for which this principle is true. Newton's second law states that the total momentum of the system is conserved if the net force on the system is zero. However, the net force on the system I chose was not exactly zero. The contact force from the table had a parallel component to the motion that was non-zero, the force due to friction. I assumed that there was negligible friction in my computer model, but it is evident that there was some force opposing the motion because the marble's rolling was not exactly at a constant speed and all of the momentum lost from the large marble was not transferred to the small marble. The interaction between the friction force and the marbles probably led to a net escape of energy from the system, which also probably contributed to the motion not being exactly what I expected. In order to see if this was true, I decided to calculate the change in translational kinetic energy due to the collision and then use this value to make an estimate for the change in internal energy of the system. For this part of the calculations, I included the table in the system along with the marbles because I knew that the total change in energy for this system was zero, since there was no external force interacting with these objects. Therefore, I knew that if the total translational kinetic energy of the marbles decreased, this energy would have been converted to internal energy of the system, whether that be in the form of rotational kinetic energy of the marbles, thermal energy between the marbles and the table, or even energy in the form of sound when the marbles collided. To perform these calculations, I used the formula kinetic energy is equal to half of the mass times the speed of the object squared. Using the speeds of the two marbles both before and after the collision, I found that the initial kinetic energy was 3.392 times 10 to the negative 4th joules, and the final kinetic energy was 2.967 times 10 to the negative 4th joules. The change in translational kinetic energy was negative 0.427 times 10 to the negative 4th joules, which indicated that translational kinetic energy was lost from the system. Since the total change in energy for the system was zero, the change in internal energy was positive 0.427 times 10 to the negative 4th joules. As I mentioned before, this increase in internal energy could have been in the form of heat as the table and the marbles increased in temperature, along with the sound caused by the marbles hitting each other. If I had wanted to go further into these energy calculations, I could have even calculated the change in rotational kinetic energy of the marbles using the moment of inertia for a sphere and figuring out the angular speeds of the marbles. I could have used this information to evaluate the total change in kinetic energy, which could have been used to determine whether or not the collision was elastic. Regardless of the conclusion, this lab has shown that the energy and momentum principles can be applied to multi-particle systems in order to make calculations about their motion.